Hi guys, today we're going to take a look at question 5 of the 2017 exam paper 1. Okay, so the function f is such that f of x equals 2x cubed plus 5x squared minus 4x minus 3. Show that x equals minus 3 is a root of f of x, and find the other two roots. Okay, so very clearly broken up into two parts. So for the first part, we're going to show that x equals minus 3 is a root. And then the second part will be find the other two roots. So we're not going to worry about the second part until we've shown that x equals minus 3 is a root. Okay, so if x equals minus 3 is a root, so x equals minus 3 is a root if f of minus 3 is 0. Okay, so let's just investigate that. So our f of x equals 2x cubed plus 5x squared minus 4x minus 3. And we want to see if we put minus 3 in for x, does it equal 0? So 2 by minus 3 cubed plus 5 by minus 3 squared minus 4 by minus 3 equals 0. Okay, so x equals minus 3 is a root. Simple enough. Nice start to the question. And now we have to find the other two roots. Okay, so we're working with a cubic, so we don't have this nice formula like the quadratic to find the roots. But we can make this a quadratic, so we know that if x equals minus 3 is a root, then x plus 3 is a factor. This is the root factor theorem. So if we divide f of x by x plus 3, then we should get some quadratic. And quadratics we can solve. We can just use the minus b formula for that. So we're going to divide x plus 3 into f of x. So we're going to use standard long division approach. X plus 3 into f of x, 2x cubed plus 5x squared minus 4x minus 3. So x goes into 2x cubed, 2x squared times. So we get 2x cubed plus 6x squared. Then minus, change sign here. Get a 0 and a minus x squared. So x goes into minus x squared minus x times. So minus x by x is minus x squared minus 3x. We bring down our minus 4x. Then we change the sign, just standard long division. We get a minus x, 0. Then we bring down our minus 3. And x goes into minus x minus 1 times. So then we multiply back, minus x minus 3, change the sign. And we get 0 as expected. So when we divide f of x by x plus 3, we get 2x squared minus x minus 1. So f of x is equal to x plus 3 times 2x squared minus x minus 1. So the other two roots, let's write this out. The other two roots of f are the roots of this polynomial here, this quadratic here, are the roots of 2x squared minus x minus 1. Okay, and now we can find the roots of this pretty easily. So if we use our minus b formula, x equals minus b plus minus the square root of b squared minus 4ac all over 2a. And then our a is 2, our b is minus 1, and our c is minus 1. Then our roots are x plus and x minus, which are minus minus 1, 1 plus the square root of minus 1 squared, 1 minus 4 times a, 2, by c, minus 1, all over 2 by a, which is 4, 2 by 2. And then our x minus is, again, 1, but this time a minus 1 minus 4 by 2 by minus 1, all over 2 by 2. 2a, 2 by 2. And so x plus equals 1 plus root 5 over 4. And our x minus is 1 minus root 5 over 4. So these are our other two roots of f. 1 plus root 5 over 4 and 1 minus root 5 over 4. Now you could put this into a calculator and get some decimal answer, but I really don't think that's necessary. These answers are perfectly okay. Now on to part B. Find the coordinates of the local maximum point and the local minimum point of f. Okay, so just a refresher, our function f is 2x cubed plus 5x squared minus 4x minus 3. Yeah. Okay, so we're looking for the local maximum. And whenever we hear local maximum, we should be thinking derivative equals 0 and second derivative is less than 0. Second derivative is less than 0. And whenever we hear local minimum, we should be thinking, again, the derivative equals 0, and the second derivative is greater than 0. Okay, so the reason that they're looking for the local maximum and the local minimum rather than just the maximum or the minimum is because we're looking at a cubic. So it doesn't really have a maximum or a minimum because it looks something like this. So it goes down all the way to minus infinity and it goes up all the way to positive infinity. So it doesn't really have a maximum or a minimum, but it does have these values here. This local maximum, which means it's bigger than anything around it, and this local minimum. And so at these points, these turning points, the derivative, the slope of the function is 0. And so that's why with this question we'll be looking at local maximums and local minimums. So let's give ourselves some space. Okay, so, well, we've got to find the derivative. If you want to allow the derivative to be 0, then we've got to find that derivative. So f prime of x equals, bring down the power, reduce it by 1, 3 by 2x squared, plus 5, bring down the power, reduce it by 1, minus 4, bring down the power, reduce it by 1, so just 4, and then a constant goes away. So we get 6x squared plus 10x minus 4. Okay, and so we want to allow this to be 0. So we want f prime of x to be 0. And so we get 6x squared plus 10x minus 4 equals 0. And so we can just divide across by 2 just to make it a bit simpler. And then we can just use the minus b formula to solve this, to solve for the x equals the x such that f of x is 0. So x plus and minus is minus b plus minus the square root of b squared minus 4ac all over 2a. And our a is 3, our b is 5, and our c equals minus 2. So if we plug this in, so our x plus is equal to minus 5 plus the square root of 5 squared minus 4 times 3 times minus 2 all over 2 by a, 2 by 3, and our x minus equals, again, minus 5 minus 5 squared minus 4 by 3 by minus 2 all over 2 by 3. And so our roots of this quadratic, the x such that the derivative is 0, are x equals 1/3 and x equals minus 2. So these are the values of f such that the derivative equals 0. But which one is the minimum and which one is the maximum? Well, we could use this second derivative test, but we actually don't need to. We can actually just plug these in to f and see which one is bigger. So if we take f of minus 2, we get 2 by minus 2 cubed plus 5 by minus 2 squared minus 4 by minus 2 minus 3, and f of 1/3 equals 2 by 1/3 cubed plus 5 by 1/3 minus 4 by 1/3 minus 3 equals 9 and minus 28 over 27. So clearly this is our maximum and this is our minimum. And so they're asking for the coordinates, so the local maximum is minus 2, the x-coordinate, and the y-coordinate is 9. And our local minimum is 1/3 minus 28 over 27. Okay, so that's our local maximum and our minimum. And just a quick, an even quicker way that you could determine which was the max and which was the min. Well, if you look at the graph that you would get for a cubic, if the first coefficient is positive, then the graph looks something like this. So it starts very small and then it gets very big, because the cube term, when x becomes large, the cube term is the only thing that matters, because it's way bigger than either the square term or the x term or the constant. And so as x gets large, this function gets dominated by the x term. So when x is really low, so like a large negative number, then we get very large negative values. And when x is very large, so a large positive number, we get very large positive values, because a large negative cubed is a very large negative, and a large positive cubed is a very large positive. So you could have just said that the first one, so the one further to the left, in this case -2, would be the maximum, because we can just see that on our graph, and the one further to the right, will, in this case 1/3, would be our minimum. But that's just let you know a little something about cubic polynomials that it might be useful to know. But these are our answers. This is all you need to give. Now on to part C. F of x plus a, where a is a constant, has only one real root. Find the range of possible values of y. Okay, now here is where knowing what the graph of a cubic looks like, or what this cubic would look like, is very useful. So our roots, we know, are let's say -3, 1 plus √5 over 4, 1 minus √5 over 4. So maybe our graph looks something like this. Something like this, okay? It's got a minimum here, a maximum here, and it's got roots here, here, and here. Okay, so unlike a quadratic, a cubic always has to have one root, because it has to hit the x-axis somewhere. Because these two lines stretch off to infinity. So how could it have only one root? Well, what it would look like if it had only one root would be something like this. So if it went up over the x-axis and then dipped, but it never quite hit the x-axis again. So this would have one root here, or an alternative would be if it looked like, if it went up but never quite hit the x-axis, went down and then went back up and then it hit the x-axis. So that would have one root here. Okay, so if we add a constant, which is what we're doing, all that does is it shifts the entire graph up or down depending on if the constant is a positive or a negative. So if we're looking at this type of graph, let's say we want to make it look like this, then we have to shift the graph up so that this stretch is all above the x-axis. And so that means we need to increase it by this amount, or well, slightly more than this amount. So we bring the minimum above the x-axis. So if the minimum here, if the minimum doesn't hit the x-axis, well then none of this stretch will. And so we know that the minimum point is minus 28 over 27. That's as far down as it goes here. So if we add 28 over 27 to the graph, or more than 28 over 27, then this stretch of the graph here will be above the x-axis. So if a is greater than 28 over 27, we will have one real root. Okay? And now let's say we want to have a graph like this. Well then similarly, we need to bring our graph down by this amount, by a little bit more than this amount. Because if this section is below the x-axis, then it will have never hit it, and we'll have something like this in the bottom right. And so how much does it take to bring our graph, to bring this stretch below the x-axis? Well, this is 9 high. This is what we figured out. It's 9 high. So we have to bring it down. We need to bring the graph down by more than 9. So a is less than minus 9 in sense. So we're bringing it down more than 9. And in that case, so if a is less than minus 9, we have one real root. Okay, so if we combine these, so if a is greater than 28 over 27, we have one real root. And if a is less than minus 9, we have one real root. So the range of values of a, which gives f of x plus a one real root, is a is less than minus 9. Let's just, a is less than minus 9, or a is greater than 28 over 27. And so this is the range of values that we're looking for. I know this is a bit of a graphical, intuitive approach, but I think that this getting a better understanding of what cubics look like and how they work is the most beneficial thing that I could get across in this video.